Hi, thank you for watching this presentation. My name is Estrada and today I'm going to show you our bidirectional platform for precise transcranial ultrasound delivery and optoacoustic monitoring of the mouse brain. If you want to perform transcranial ultrasound experiments in mice, you will find yourself with a bulky ultrasound transducer that doesn't allow you to image the already small mouse brain. We solve this problem by adapting our optoacoustic tomography system to also deliver ultrasound. The core of our system, called POTUS, here on the left, is a spherical matrix array of 112 channels, which works with custom electronics that allow this emission and detection of ultrasound. To give you a perspective on the improvement that one would expect from such an array, here you can see the outcome and the focusing performance of a single transducer at 0.5 MHz, a linear array at 5 MHz, and what you obtain with the POTUS system, which is a very tiny focal spot. The optoacoustic imaging performance of POTUS is in the order of 200 microns in resolution. Here you can see these two plots for axial and lateral resolutions. Here at the center you can see an example of imaging using a wavelength of 488 nanometers. And although the imaging depth is not great, this wavelength is very important for calcium imaging using fluorescent indicators. And finally on the right you can see that you can reach deeper in the mouse brain if you use longer wavelengths. So now let's move on to the characterization of the ultrasound emission. Here on the left you see a comparison between the measurements and simulation. For the lateral cross-section the agreement is very good, although for the axial cross-section you can see that the measurements and the simulation agree reasonably well, but they don't match exactly. The model we used was a linear model, and I think the discrepancy comes from nonlinear effects. We observe a higher second harmonic generation when we use the full array in comparison to when we just split the emission to 8 different groups of transducers and then we add the contribution of each group in the computer. So this is very nice. It's a very small spot. What happens when the ultrasound has to cross the skull? The skull really affects the focusing performance, and even at 3 MHz, which one would think is a very low frequency, the peak pressure decreased by a factor of 4. However, although the focus is smeared, we are able to keep the lateral focusing at least always below 0.5 millimeter. And how can we use this to measure something in the mouse brain? Well, my former colleague Ben McLarney showed how to perform how to monitor hemodynamic changes in the brain. So you can track hemoglobin, for instance, and measure total hemoglobin, oxygenated hemoglobin, and deoxygenated hemoglobin in the mouse brain. And we do this by using different wavelengths for the laser emission, and we repeat this sequence over and over again. And then we allocate time for the stimulation duration, and then for the optoacoustic detection we detect every single laser shot at each color, and then we have an effective frame rate which is determined by the repetition frequency of the laser and the number of wavelengths we are using. So to conclude, POTUS is a bidirectional platform for preclinical studies. It has high resolution and it opens new possibilities for image-guided transcranial ultrasound applications such as neuromodulation and targeted BB opening. I would like to conclude by thanking my colleagues and co-authors and funding agencies. Thank you very much for your attention.